Hi, today we're going to be talking about chemical reactions. All right, finally. Um, Basically, a chemical reaction is the process by which one or more pure substances are changed into one or more new pure substances by the reorganization of component atoms. All right, so this is where we're talking about how, remember, pure substances are either compounds or pure elements. And if you, when you're starting off with some pure substances, the bonds will break, new bonds will form, and you'll end up with new pure substances. This is also known as a chemical change. All right. Now, chemical reactions involve a rearrangement of the ways atoms are grouped together. The products of a reaction are made up of the same number and kinds of atoms as were present in the reactants. And remember, products are the substances, the new substance that are formed in a chemical reaction. It is always to the right of the reaction arrow, whereas the reactants are the starting substances in a chemical reaction shown to the left of the reaction arrow. And what happens is that the bonding patterns of atoms are merely rearranged. All right, bonds are broken and new ones are formed. It is you cannot destroy or make new atoms in this process, at least not in a chemical reaction. Remember, that takes a nuclear reaction to do. But in a chemical reaction, the bonding patterns are merely rearranged. All right, so you end up with the same number and types of atoms that are present in the beginning must be there at the end, no matter what. All right, and that's why we can balance equations. But now, how can you tell that a chemical reaction has actually occurred? Well, it can be difficult sometimes because most of the following indicators can be produced physically. All right, so there are a number of indicators that you can look for, and think of these kind of like clues that, hey, look, if I see this, probably a chemical reaction has occurred, but not necessarily. First of all, a color change in the reaction system. Now, I'm not talking about an obvious color change, like if you have green paint, if you have blue paint and you mix it with yellow paint, it ends up with green paint. I'm saying, well, what if you have a blue solution and you mix it with a yellow solution and it ends up, I don't know, orange or red or something unexpected. So in a way, it's kind of like an unexpected color change. All right. Next is the formation of a solid precipitate. Now, precipitate, remember, is a solid that comes out of solution. When you have a couple of reactants, they come together. If one of the products is a solid that will not dissolve in water, it will come out as a precipitate. Now, when you see a precipitate, if you're actually doing this experiment, what you usually see is you have a couple of clear solutions. They may be colored, but still clear. When you mix them together, if it gets all cloudy, that means that a precipitate has indeed formed, okay? Now, another type is the evolution of a gas. Bubbles form. So like if you have a metal and you put it in a solution, you start seeing a bunch of bubbles coming. That's a good example of an evolution of a gas. Now, a fourth one is the evolution or absorption of heat. So if you can feel it, if you can feel that it gets hotter or if it gets colder, then that is a good indicator that a chemical reaction has taken place. Remember, if it gets hotter, that means it's releasing energy, it's exothermic. If it is getting colder, it's absorbing energy, and that means it's endothermic. And it could also emit light. Now, it could emit light as in a flame, where it does both production of heat and the emission of light, or it could be something like a glow stick, where it just emits light. All right. Now, since each and every one of these can be, as it were, reproduced physically, all right. For example, the whole, hey, look, you got yellow paint, blue paint, boom, it makes green. Is that a color change because of a chemical reaction? No, that's actually a physical change. Formation of a solid precipitate. Well, what if you get water and make it really cold? Well, it turns into a solid. Is that a precipitate? Again, it's hard to tell sometimes. Evolution of a gas. I mean, heck, you open up a soda, open up a Sprite or a 7-Up or something, and it produces a bunch of bubbles. That's physical because it is the gases are coming out of solution. It's not because there's a chemical reaction. And evolution or absorption of heat. If you turn on a heater or a toaster, if you look inside a toaster with the little wires and they start glowing, is that a chemical reaction because it's giving off heat and light? No, it's not. That's just a physical process. So all of those can be reproduced physically, and it can be kind of confusing at times. And therefore, the only definite proof that a chemical reaction has in fact taken place is the formation of a new pure substance from the atoms present in the reactants. So you have to test it and see if you end up with something new. It's only 100% surefire way. Now, chemical equations. A chemical equation represents a chemical reaction. It uses formulas of the starting substances that react and the new substances that are formed. So it gives the chemical equations, chemical formulas of the reactants and products, and it puts them in the appropriate order. Now, basically, it describes the type and number of atoms that are rearranged during a reaction. Remember, reactants are shown to the left of the arrow, products are shown to the right. And they are separated, individual reactants are separated with a plus sign, just like individual products are separated with a plus sign. Now, you could have something like this, which is known as a skeletal equation, or an unbalanced chemical equation that just tells you what the reactants are and what the products are. You could have a word equation that doesn't use formulas. It just uses words and might just describe it in a sentence, like methane reacts with oxygen to produce carbon dioxide and water. But the best way of looking at it, a best representation would be a balanced chemical equation. Because not only does a balanced chemical equation give you what the reactants and products are that are part of the reaction, but it also indicates how many, how much. And that is a much more realistic representation of the chemical reaction. Now, another thing that it can do is it can give you more information. All right? Think of equations kind of like a recipe in that they show the types and amounts of reactants and also the expected yield of products. I mean, if you've ever made chocolate chip cookies from scratch and you're looking at a recipe, it tells you, first of all, what the reactants are. You got your flour and sugar and egg and salt and all that good stuff. And it tells you the amounts, all right? How much flour, how many eggs, and so forth. And also it tells you the expected yield. Yield is an old-fashioned way of saying product. If it is a noun, it's product. If it is a verb, then it is to produce. To yield something is to produce. So the expected yield of products is like, how much do you produce? What do you produce? How many chocolate chips do you actually make? All right, or can you make in a recipe? So equations can also indicate the reaction conditions and the physical states of the reactants and products. Some reactions do not occur unless you also add heat. Some reactions need certain conditions that need to be met. All right. You will often see, for example, the physical states. These are often in a chemical reaction equation, and they come at the end of each substance, and they're like a subscript and in parentheses. An S for solid, L for liquid, G is in its a gaseous form. AQ indicates that it has been dissolved in water. In other words, an aqueous solution. Now, aqueous solutions are often required for ionic compounds, for example, to react with each other. As solids, they wouldn't be able to react. But when you dissolve them in water, the individual ions can have access to each other, and that allows for the chemical reaction to occur. So it often will say what states of matter the substances must be in. Okay. For example, here, solid potassium reacts with liquid water to produce hydrogen gas and potassium hydroxide solution. In other words, dissolved in water. That's why it has the AQ after it. All right. All right. So now I wanted to make sure you guys understand this concept known as moles. So we're going to kind of shift gears here and start talking about that. Hi. Today we're going to be talking about something very special in chemistry, moles. All right. And the basic concept of dealing with moles is in chemistry, as you know, we deal with very, very, very small particles. All right. And in order to have enough small particles that we can actually manipulate them and deal with them in the real world, we need to group them together in large quantities, extremely large quantities. And that, dear children, is where we get the concept of moles. You see, atoms, individual atoms, have very, very tiny masses, okay? And I mean, we're talking incredibly small. Just to give you guys a brief idea of how small an atom really is, if you were to consider, imagine the atoms in the eyeball of a mouse, okay? Think of how small a little eyeball of a little mouse is. The atoms that make up that eyeball are roughly the same scale size-wise as that eyeball compared to the overall world, to the overall Earth, okay? So atom is to eyeball as eyeball is to the Earth, just to give you guys a sense of scale. And since they are so small, measuring them in grams is actually completely useless, really, okay? Therefore, chemists have devised a unit specifically for individual atoms, and that is known as the Unified Atomic Mass Unit, or just U for the symbol, okay, or for the unit. And it is approximately 1.66 times 10 to the negative 24th. Sorry. Oh, dog is saying hi. This is Murray. So 1.66 times 10 to the negative 24th grams. Now, just so you know, that is the mass of a single proton or neutron. So if you're trying to figure out the mass of an individual atom and it has, let's say, 6 protons and 8 neutrons, you just add them up. 6 plus 8 is 14, and you would say that individual atom has a mass of 14 U's, okay? Or Unified Atomic Mass Unit. Now, so they're measured, this is what the mass numbers are. So when you have like carbon 14, the C14, that's what it's talking about, okay? Now, atomic mass, this is what we actually see written out on the periodic table, all right? The atomic mass is different, okay? Atomic mass is the weighted average of the masses of all the different isotopes of an element, all right? Now, as you guys know, different atoms or different elements can have different number of neutrons and therefore different mass numbers. All right. Once again, carbon, for example, carbon has several different isotopes. That's when you have the same element but with different number of neutrons and therefore masses. For example, one is carbon-12. It has 6 protons and 6 neutrons for a grand total of 12 U's. But there's also something like carbon-14. Carbon-14 has 6 protons and 8 neutrons. Now, it's still carbon because it has 6 protons. That's what defines what an element is the number of protons. So you would say that it has a mass of 14 and its number, C or carbon 14 indicates that mass. Well, when you look on the periodic table, all right, the number that you look on there for carbon is not either 12 or 14. It's actually like 12.011. All right, and it's a fraction. All right, it's a decimal. And the reason why is because it takes into account the masses of the different isotopes in an element and the relative abundances, how common they are. Okay, and this is why atomic masses are not whole numbers. Now, you could, for ease sake, maybe round them off to a whole number, but that's not what we do in here, okay? So basically, what you need to do when reading atomic masses off of the periodic table, always go to 2 places past the decimal place, okay? Always go to 2 places past the decimal, so that carbon, instead of 12.011, you go to 12.01 when you read it, all right? So you have the number, decimal, and then 2 more places. You round off after that second place, all right? So, for example, hydrogen on the periodic table says it has a mass of 1.008, but you should read it as 1.01 U's, okay? Now, by the way, real fast, why is it, for example, carbon is 12.01. Well, yes, it takes into account the fact that there's carbon 12 atoms and carbon 14 atoms, but it's carbon 12 is by far the most common isotope of carbon. That's why it kind of skews the average much closer to 12. Yes, there's a few carbon 14s and carbon 13s, even some carbon 11s. But when you look at all of them, there are by far more carbon 12s, and that's why the atomic mass, is 12.01, okay? Now, as I was saying, since atoms are so incredibly small individually, we need to have enough of them that we can actually deal with them. I mean, if you're a chemist and you want to react some hydrogen with oxygen, you're not going to take a hydrogen molecule and an oxygen molecule and kind of cram them together or anything. It doesn't work that way. You need to have a large enough amount that you can actually deal with them in the real world. And that's where the mole comes into it. Now, the mole is defined as the number equal to the number of carbon 12 atoms in exactly 12 grams of pure carbon 12. We'll get to that in a minute, okay? We'll get to what that really means. But basically, the mole is a really large number, all right? It's a very large number. Large enough so that you have enough atoms that you can actually deal with them in the real world, okay? Like the term dozen, it represents a specific number of things. Now, it is used to represent many small atomic-sized representative particles. Now, the term representative particles is like the smallest size something can take, a unit, smallest unit in which a substance naturally exists in. So if it is something like helium is found in atoms. However, hydrogen, since they're diatomic, those smallest ones are molecules. It could be in individual ions, like like oxide ions, O-2. That could be found in ions, or it can be what are known as formula units. If you're dealing with something like an ionic compound, like salt, those lowest, smallest units are formula units, but they're all representative particles. And you would, 1 mole is basically a large number of those. Well, how large? Really flippin' large. 1 mole of anything contains 6.022 times 10 to the 23rd units of that substance, okay? That is a really big number. Basically, imagine a 6, a 0, 2, 2, and then 20 zeros after it, all right? So you need that many of them in order to get enough that you actually can deal with and see in the real world. So a dozen is 12. A mole is 6.022 times 10 to the 23rd. Now that is known as Avogadro's number or Avogadro's constant. And he was an Italian scientist that figured out this number. And you're going, well, wait a second. What's so special about that number? Why does it have to be that specific number? I mean, theoretically, what if you had 1 times 10 to the 24th? Wouldn't you have enough atoms to be able to see them and work with them? Yeah. But the beauty of this number is if you have exactly that number of U's, all right, of, let's say, protons or neutrons or anything that weighs one unified atomic mass unit, if you have 1 mole of those, then it would weigh exactly 12 grams. You see, it is the conversion that we use to go from the realm of AMUs, or U's, all right, sometimes they're called AMUs, and it goes from that realm to things that are measured in grams. So whatever it weighs in U's individually, whatever the atom or molecule weighs individually in U's, that's what it's going to weigh. If you have a mole of them, that's what it's going to weigh in grams. Okay, that's why the definition of this, it was set by saying, all right, if you have 12 grams of carbon 12 atoms, all right, if you have exactly 12 grams of carbon 12 atoms, that's how many a mole is going to have. Whatever number of atoms make 12 grams, that's how many is going to be 1 mole. And it turned out, after many painstaking measurements, he figured out that it was equal to 6.022 times 10 to the 23rd. All right, so a sample of an element with a mass equal to that element's average atomic mass, expressed in grams, contains 1 mole of atoms. And by the way, when you use moles as a unit, just use MOL. I know it doesn't save a whole lot, but that way it's kind of like the word deer. All right, you can say 3 moles and just write 3 MOL. And you don't have to worry about an ES or anything like that. It works for singular and for plural. And just to give you guys an idea, if you look at 1 mole of any of these items, these are their masses in grams. All right. Well, if you look on the periodic table, this is what the mass, the atomic mass of aluminum is, or this is the atomic mass of gold. All right. That's what all of these are equal to. And it makes it so much easier. So individually, a gold atom weighs 196.97 unified mass units, but a mole of gold atoms weighs 196.97 grams. Sorry about jumping around like that, but that should give you everything you need to know about chemical reactions, chemical equations, and about the mole. At least enough for now. All right. Good luck, and if you have any questions, please come to tutorial. Bye-bye.